Imagine that the universe is not completely silent. Imagine that the darkness above us is not just empty black space, but a frozen ocean of ancient light, carrying messages from a time before Earth, before the Sun, before the Milky Way, before even the first star had opened its eye in the dark. Now imagine that inside this ancient light, scientists found a strange mark, a colder patch, a quiet wound in the sky, so unusual that even after years of study, even after some of the most powerful space telescopes and sky surveys ever built, no one can say with complete confidence what caused it. Is it just a rare accident in the cosmic pattern? Is it the shadow of a gigantic empty region of space? Is it a fingerprint from the birth of the universe itself? Or is it something even stranger, something that touches the deepest questions about reality, time, space, and whether our universe is the only one? Before we travel into this cold mystery, ask yourself one question. If the universe left behind a baby picture of itself, and in that picture there was one strange dark mark that did not fit the expected pattern, would you ignore it? Or would you wonder whether the universe was trying to tell us something? And as we drift into this deep cosmic story, if you enjoy slow, realistic, science-based journeys into the strange places of space, then quietly like this video, subscribe to the channel and write in the comments what you think the cold spot really is: a cosmic accident, a giant void, or a clue to physics we still do not understand. The story begins not with a telescope looking at stars, but with a telescope looking behind stars, behind galaxies, behind the great glowing structures of the universe, all the way back to the oldest light we can observe. This light is called the cosmic microwave background. It is not ordinary starlight. It is not light from galaxies. It is not the glow of dust. It is the leftover heat of the early universe stretched by cosmic expansion until it became microwave radiation. Today it fills all of space. It surrounds you right now. It passes through your room, through the walls, through the air, through your body like a ghostly ocean of ancient photons. It is almost perfectly uniform, almost the same temperature in every direction, about 2.725 degrees above absolute zero. But the word almost is where the mystery begins. In the earliest moments after the Big Bang, the universe was not yet a calm, dark place. It was hot, dense, bright, and full of charged particles. Light could not travel freely because it kept bouncing from electrons, like sunlight trapped inside a glowing fog. Space itself was expanding, cooling, stretching. Then, about 380,000 years after the beginning, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, light was no longer trapped in the cosmic fog. Photons could move freely across the universe. Those photons are still traveling today. They are the cosmic microwave background, the CMB, the afterglow of creation. When we look at the CMB, we're not looking at the universe as it is now. We're looking at the universe when it was a baby, long before stars and galaxies existed. But this baby picture is not perfectly smooth. It has tiny hot and cold spots, slight temperature differences, incredibly small variations measured in microkelvin, millionths of a degree. These variations are not errors. They are some of the most important clues in all of science. They show where matter was slightly denser or slightly thinner in the early universe. Those tiny differences later grew under gravity into galaxies, clusters, superclusters, and the great cosmic web. Every galaxy we see today, every star, every planet, every atom in your body owes its existence to those tiny wrinkles in the ancient light. Without them, the universe might have remained smooth forever, a featureless sea of gas and radiation, beautiful perhaps, but empty of structure, empty of worlds, empty of life. Scientists expected the CMB to contain these tiny variations. In fact, modern cosmology depends on them. The standard model of cosmology says that the early universe experienced a rapid expansion known as inflation, a brief but powerful stretching of space that enlarged tiny quantum fluctuations to cosmic size. These fluctuations became the seeds of structure. In this picture, hot and cold regions in the CMB should appear like a kind of random cosmic noise, a pattern with statistical rules, not perfectly predictable in every spot, but predictable in overall behavior. Some patches should be slightly hotter, some should be slightly colder, some should be large, some should be small. But when scientists mapped the CMB carefully, one patch looked too strange to ignore. This strange patch became known as the CMB Cold Spot. It lies in the direction of the constellation Eridanus, an enormous region of sky that appears colder than average compared with the surrounding cosmic microwave background. The temperature difference is tiny by everyday standards, only tens of microkelvin, far less than any human body could feel, far less than any ordinary thermometer could notice. But in cosmology, such tiny differences are enormous clues. The mystery is not that this region is physically a frozen cloud. It is not a place where astronauts would suddenly freeze more than in other parts of space. It is a pattern in ancient radiation, a colder than expected mark in the first light of the universe. At first it might sound simple. The universe has cold patches. This is one cold patch. Why should anyone care? But the cold spot is not just a little colder than average. It appears unusually large and unusually cold compared with what scientists expected from a simple random universe. It is not impossible in the standard model, but it is uncommon, and science becomes very alert when something is uncommon in the right way. A rare pattern can be meaningless, like seeing a shape in clouds, but sometimes a rare pattern is a doorway. Sometimes it is the first clue that a theory is missing something subtle. The first major maps of this ancient light came from satellites designed to measure the CMB with incredible precision. Earlier missions had already detected the microwave background and its tiny variations, but the Wilkinson Microwave Anisotropy Probe, known as WMAP, gave scientists a detailed full-sky map. There, among the expected hot and cold patches, the cold spot stood out. Later, the European Space Agency's Planck satellite mapped the CMB with even greater precision. Planck also saw the feature. That mattered because if only one experiment saw it, scientists might suspect an instrument problem, a processing artifact, foreground contamination, or some local effect from our galaxy. But when different instruments and different analyses pointed to the same strange region, the mystery became harder to dismiss. Still, being real in the data does not automatically mean being revolutionary. This is where the story becomes delicate. Cosmology is filled with patterns, and human minds are powerful pattern-making machines. If you stare at a random map long enough, you may find shapes that feel meaningful. You may find a cold region, a hot ring, an alignment, a void, a face, a scar, a symbol. Scientists know this danger very well. So when they study the cold spot, they do not simply ask, does it look strange? They ask, how strange is it statistically? How often would a universe like ours naturally produce something like this? That question is much harder than it sounds. The universe gives us only one observable sky. We cannot rerun the Big Bang a million times and see how often cold spots appear. We cannot step outside the universe and compare our CMB with many other universes. We have one sky, one cosmic microwave background, one sample of the largest scales. This limitation is called cosmic variance. It means that on very large scales our ability to judge what is normal is limited because we only have one universe to measure. If the cold spot is a rare random fluctuation, then it may be like drawing one unusual card from a cosmic deck. Strange? Yes. Impossible? No. And because the universe is vast, rare things must happen somewhere. But the human mind is not satisfied with, maybe it is random. We look at the cold spot and wonder whether something caused it. One of the most discussed possible causes is a supervoid, a huge region of space with fewer galaxies and less matter than average. To understand this idea, imagine a photon from the CMB traveling billions of years across the universe. On its way, it passes through regions where gravity is stronger or weaker. Gravity affects the energy of light. In a static universe, light falling into a gravitational well gains energy, and light climbing out loses energy, and the two effects can cancel. But our universe is expanding, and dark energy changes how gravitational structures evolve over time. Because of this, light passing through a large void can lose a small amount of energy. This is related to the integrated Sachs-Wolf effect. A cosmic void is not truly empty. Space inside a void still contains dark matter, gas, radiation, and perhaps galaxies. But compared with dense cosmic regions, it has less matter. The universe on the largest scales looks like a web. Galaxies gather along filaments and walls, clusters sit at intersections, and vast underdense spaces lie between them. These voids can be enormous, hundreds of millions of light-years across. If a very large void existed in the direction of the cold spot, perhaps CMB light passing through it could become slightly cooler, leaving the cold mark we observe. This idea became especially interesting when some studies suggested an underdense region in the direction of Eridanus, sometimes called the Eridanus supervoid. If true, this would make the cold spot less like a mysterious wound from the birth of the universe and more like a secondary effect, a cold imprint created as ancient light travelled through a giant cosmic emptiness. That would still be amazing. Imagine light born when the universe was 380,000 years old, travelling for nearly the entire age of the cosmos, then passing through a vast region with fewer galaxies, losing just a little energy, and arriving at our detectors slightly colder than expected. The cold spot would not be a message from the beginning alone, but a message written twice, once in the early universe and once during the light's journey through the cosmic web. But the twist is that the supervoid explanation does not fully solve the problem. Some observations support the presence of an underdensity in that direction. Other analyses suggest that the void is not deep enough or not large enough to explain the entire cold spot. The integrated Sachs-Wolf effect is real, but it is usually subtle. To produce a feature as strong as the cold spot, the void would need to be unusually large, unusually empty, or arranged in a very specific way. Some researchers argue that the observed structure can contribute to the coldness, but cannot account for all of it. Others argue that once uncertainties are considered, the connection is not strong enough to be convincing. So the supervoid stands like a suspect in a cosmic investigation, present near the scene, scientifically plausible, but not proven guilty. Now the mystery deepens, because if the cold spot is not completely explained by a supervoid, we must return to the ancient universe itself. Perhaps the cold spot was already there at the beginning, written into the CMB at the moment the universe became transparent. If that is true, then the cold spot may be connected to primordial physics, to the conditions of the early universe, to the nature of inflation, or even to processes beyond the standard model. But scientists must move carefully here. The early universe is a place where imagination can easily outrun evidence. A mystery does not automatically mean exotic physics. Still, it invites the question. One possibility that has been discussed is that inflation was not perfectly simple. In many textbook explanations, inflation is smooth and elegant. Space expands rapidly, quantum fluctuations stretch outward, and the universe becomes almost uniform with tiny random variations. But inflation may have been more complicated. The field driving inflation may have had features, transitions, or unusual behavior. If so, the early universe might have produced anomalies on very large scales. The cold spot could then be a fossil of a strange event during inflation, a frozen memory of a moment when the rules changed slightly. This is fascinating because the CMB is one of our only direct observational windows into inflation. We cannot build a machine on Earth that recreates the entire early universe. We must read the sky. Another idea involves cosmic textures or topological defects. In some theories, as the early universe cooled, fields may have settled into different configurations in different regions, creating defects in the fabric of the field, somewhat like cracks forming when water freezes into ice. Cosmic strings, domain walls, monopoles, and textures have all been considered in different theoretical contexts. A cosmic texture could, in principle, create a hot or cold spot in the CMB as it collapses or unwinds. Some researchers once suggested that the cold spot might be the signature of such a texture. But again, this remains speculative. There is no strong accepted evidence that a cosmic texture caused the cold spot, and models must fit not just one anomaly but the whole sky. Then there is the most dramatic idea of all, the one that captured public imagination. Perhaps the cold spot is a bruise from another universe. In some versions of inflationary cosmology, our universe might be one bubble in a larger multiverse, where other bubble universes also form. If two bubble universes collided in the distant past, the collision could leave a circular imprint in the cosmic microwave background. Some people have suggested that the cold spot might be such an imprint. It is a breathtaking thought, a faint cold mark in the sky, as evidence that our universe once touched another. But this idea must be treated with extreme caution. It is not proven. It is not the mainstream explanation. It is not something scientists can confidently claim. It is a speculative possibility, interesting because it connects the cold spot to deep theoretical ideas, but weak because evidence for it is not decisive. The cold spot teaches one of the most important lessons in science. Mystery is not permission to believe anything. Mystery is a reason to measure more carefully. A strange feature in the sky can inspire wild possibilities, but the job of science is to separate what is possible from what is supported. The cold spot could be random, it could be partly caused by a supervoid, it could be a trace of early universe physics, it could be a combination of effects, or it could eventually become less mysterious as better data and better statistical methods are developed. The honest answer is not simple. Scientists still cannot give one final explanation that everyone accepts. What makes the cold spot so haunting is that it lives at the border between certainty and uncertainty. We are certain that the CMB exists. We are certain it contains tiny temperature fluctuations. We are certain that the cold spot appears in major CMB maps, but we are not certain whether it is truly beyond what the standard model can naturally produce. We are not certain whether a supervoid explains it. We are not certain whether it points to new physics. It is a real feature, but its meaning is still unclear, and that is why it remains one of the most interesting anomalies in modern cosmology. To feel the scale of this mystery, imagine holding a map of the whole observable universe, not as it looks now, but as it looked when it was less than 500,000 years old. Every tiny color difference on that map represents a slight difference in temperature and density. These differences are so small that they seem almost nothing, but over billions of years gravity amplified them into everything. In one direction, there is a cold region that seems too large, too quiet, too empty in temperature. It is not shouting, it is whispering. Yet that whisper has reached some of the most advanced minds in physics. The CMB itself was once a prediction. Long before it was precisely mapped, scientists realized that if the universe began hot and dense, there should be leftover radiation from that early fire. In 1965, Arno Penzias and Robert Wilson detected a strange microwave noise, not realizing at first that they had found the afterglow of the Big Bang. Later missions measured it with increasing precision. COBE showed that the CMB had an almost perfect blackbody spectrum and detected its tiny anisotropies. WMAP refined the picture. Planck sharpened it even more. With every improvement, the universe became more readable, like an ancient manuscript slowly coming into focus. And yet, better data did not erase every puzzle. In fact, sharper maps made some puzzles more visible. The cold spot is part of a wider family of large-scale anomalies in the CMB. There are discussions about alignments of low multipoles, hemispherical asymmetry, and other unusual features on the largest angular scales. None of these anomalies alone has destroyed the standard model of cosmology. The standard model remains extremely successful. It explains the CMB power spectrum, the abundance of light elements, the expansion of the universe, the distribution of galaxies, and many other observations with remarkable accuracy. But the anomalies remind scientists that success does not mean complete understanding. The standard cosmological model is sometimes called lambda CDM. Lambda represents dark energy, often associated with the cosmological constant, and CDM stands for cold dark matter. This model says the universe is made mostly of dark energy and dark matter, with ordinary matter making up only a small fraction. It also assumes that the universe is statistically homogeneous and isotropic on large scales, meaning that when viewed at enormous distances, it should look roughly the same in every direction. The CMB is one of the strongest supports for this model, but if the cold spot or other anomalies were proven to be non-random and primordial, they could suggest that the universe has more structure, more complexity, or more directional behavior than the simplest model predicts. Still, the phrase, "scientists cannot explain," should not be misunderstood. It does not mean scientists have no ideas, it means no explanation has become clearly dominant and fully accepted. Science often lives in this state. A mystery may have several possible explanations, each with strengths and weaknesses. The cold spot is not like a magic hole in space. It is not a portal. It is not evidence that physics has failed. It is an anomaly in precision cosmology, a subtle but persistent feature that asks whether our statistical understanding of the early universe is complete. Let us slow down and look more deeply at why a cold spot in the CMB can exist at all. In the early universe, slightly denser regions had stronger gravity. Photons climbing out of those regions lost some energy, appearing slightly colder. Other effects also contributed, including motion of the plasma and gravitational potentials. The final CMB pattern is a combination of early sound waves in the hot plasma, gravitational redshift, density fluctuations, and later effects along the line of sight. The CMB is not a simple photograph in the ordinary sense. It is a layered physical record full of information about matter, radiation, geometry, and time. Before the universe became transparent, ordinary matter and radiation were coupled together in a hot plasma. Gravity tried to pull matter into denser regions while radiation pressure pushed back. This created oscillations like sound waves in the early universe. These acoustic oscillations left a pattern in the CMB. The sizes and strengths of these patterns reveal the universe's contents and geometry. From them, scientists can infer the amount of ordinary matter, dark energy, and the age of the universe. That is why the CMB is often called a cosmic Rosetta Stone. It translates tiny temperature variations into cosmic history. The cold spot sits on top of this vast mathematical structure. It is not studied in isolation only as a pretty mark on a map. Scientists examine it through statistics, simulations, wavelet analyses, sky masks, foreground removal methods, and comparisons with galaxy surveys. They ask whether galactic dust could contaminate the signal. They ask whether radio sources or emission from our own Milky Way could affect it. They ask whether the method used to identify it makes it appear more significant than it really is. They ask whether looking for anomalies after seeing the data creates a look elsewhere effect, where something seems unlikely only because we selected it after the fact. This look elsewhere effect is very important. Suppose you throw 1,000 coins and then notice that somewhere in the sequence there are 10 heads in a row. If you had predicted exactly that location before throwing, it would be very surprising. But if you search the whole sequence after the throw, finding some unusual cluster becomes less surprising. In cosmology, the sky has many possible features. If scientists search for enough types of anomalies, they will find something that looks odd. So the cold spot's significance depends partly on how the question is framed. Was this exact feature predicted before observation, or was it noticed after scanning the data? The answer affects how mysterious it is statistically, and yet, even after these cautions, the cold spot refuses to become boring. It remains strange enough to study. It remains visually striking on CMB maps. It remains connected to real questions about voids, large-scale structure, and early universe physics. It is not a solved illusion. It is not a confirmed revolution. It is suspended in between, and that is exactly why it fascinates scientists. Some mysteries are powerful because they are loud. The cold spot is powerful because it is quiet. If you could travel in the direction of the cold spot, you would not eventually reach a blue, frozen patch of space. There would be no wall, no border, no sign saying cold spot begins here. The CMB cold spot is a direction on the sky, a pattern in radiation arriving from the edge of the observable universe. Along that line of sight, you would pass through nearby stars, interstellar gas, the halo of the Milky Way, intergalactic space, galaxies, voids, perhaps underdense regions, and finally the last scattering surface, the ancient sphere from which CMB photons last scattered before beginning their long journey. The cold spot is not one object at one distance. It may involve the early universe, the space between, or both. That is part of what makes it difficult. When we look at the sky, we see everything projected onto a two-dimensional sphere. A cold region in the CMB could be caused by conditions at the last scattering surface, or by structures between us and that surface, or by contamination from foreground sources, or by statistical chance. Disentangling these possibilities is like hearing a faint sound in a vast forest and trying to determine whether it came from nearby leaves, a distant river, or the echo of a storm long gone. The supervoid idea gained attention because it offers a line-of-sight explanation. If there is a huge underdense region between us and the CMB in that direction, it could affect the photons after they left the early universe. Galaxy surveys can test this by counting galaxies and mapping matter distribution. But mapping such enormous volumes is difficult. Surveys have limits. They may not cover every distance equally well. Some galaxies are too faint to detect. Dust can obscure regions. Photometric redshifts have uncertainties. The true three-dimensional structure of the universe is hard to reconstruct. so even the void itself becomes a matter of measurement and interpretation. A void large enough to be called a supervoid is not a simple spherical bubble. Real cosmic voids can be irregular, connected, layered, or composed of multiple smaller underdense regions. Depending on how researchers define and measure the void, its properties can change. One analysis may find a significant underdensity, another may find a shallower structure. One may argue it is aligned with the cold spot, another may argue the alignment is not enough. This is how science progresses, not by instant certainty, but through competing interpretations tested against better data. The integrated Sachs-Wolf effect is also subtle, because it depends on the evolution of gravitational potentials in an expanding universe. In a universe dominated only by matter, large gravitational wells and hills remain more stable over time. But in a universe with dark energy, cosmic expansion accelerates, and gravitational potentials can decay. When CMB photons cross these evolving potentials, they can gain or lose a little net energy. This effect is useful because it provides evidence related to dark energy and large-scale structure. But it is weak. Detecting it often requires statistical correlations between CMB maps and galaxy surveys. Using it to explain a single dramatic cold region is challenging. If the supervoid contributes only part of the signal, then the cold spot may be a combination mystery. Perhaps the early CMB already had a moderately cold fluctuation, and later the photons passed through an underdense region that made it slightly colder. Together, a rare primordial fluctuation and a late-time void effect could produce something more unusual than either alone. This kind of layered explanation is scientifically reasonable. The universe often does not provide single-cause stories. It creates features through multiple processes stacked across time. There is something beautiful about that possibility. The cold spot could be a collaboration between infancy and old age, between the baby universe and the mature cosmic web. The first part of the coldness may have been born before galaxies existed. The second may have been added as the light crossed billions of years of expanding space. A signal from the beginning may have been modified by the universe it helped create. That is a twist worthy of deep cosmology. The ancient light-shaped structure, and later structure reshaped the ancient light. To understand why scientists take such tiny signals seriously, remember that modern cosmology is a precision science. We are not merely guessing that the universe is old and large. We measure its age, composition, expansion rate, curvature, and structure using multiple independent methods. The CMB is one of the cleanest sources of information because it comes from a time when the universe was simple compared with today. But simple does not mean easy. The physics is deep and the data analysis is complex. A temperature difference of a few millionths of a degree can carry information about the entire cosmos. When Planck measured the CMB, it gave scientists one of the most accurate maps ever made of the early universe. It confirmed that the standard model works astonishingly well. The pattern of acoustic peaks in the CMB power spectrum matches lambda CDM with remarkable precision. But Planck also confirmed that some large-scale anomalies seen by WMAP did not simply disappear. The cold spot remained. This created a strange emotional balance in cosmology, triumph and discomfort at the same time. The model is powerful, the data is beautiful. And yet, in the corner of the ancient sky, something still looks odd. Some scientists are cautious to the point of skepticism. They may say that the cold spot is interesting but not enough to demand new physics. They may point out that the statistical significance is not overwhelming after accounting for the look elsewhere effect. They may argue that rare fluctuations happen and the universe is allowed to be imperfectly ordinary. This view is important because it protects science from overreaction. Not every anomaly is a revolution. Many anomalies fade with better data, better methods, or better understanding. Other scientists are more intrigued. They may argue that large-scale CMB anomalies together hint at something beyond the simplest assumptions. They may not claim proof, but they believe the patterns deserve deeper investigation. This view is also important because science advances by paying attention to uncomfortable details. If every anomaly were dismissed too quickly, some discoveries would never happen. The history of science is full of tiny discrepancies that later became doorways. The orbit of Mercury leading to general relativity, black body radiation leading to quantum theory, the expansion of the universe transforming cosmology. Of course, many discrepancies also vanish. The challenge is knowing which ones matter. The cold spot sits exactly in that uncomfortable territory. It is not strong enough to force a new theory, but it is unusual enough to keep appearing in papers, discussions, and public fascination. It is like a single strange note in a symphony that otherwise plays almost perfectly. The note may be random noise, it may be a musician's slip, or it may reveal that the composition has a hidden theme we have not recognized. Let us imagine the early universe again, not as an explosion in space, but as space itself expanding. There was no center where everything flew outward into emptiness. Everywhere was hot, everywhere was dense. Space expanded everywhere. The cosmic microwave background comes from all directions because every direction looks back to a time when the universe was filled with glowing plasma. When we see the CMB, we see a spherical shell around us, not because we are central in the universe, but because light has had a finite time to reach us. Every observer in another galaxy would see their own CMB sky, centered on themselves, with their own last scattering surface. This means the cold spot is part of our observable universe's particular view. Another observer far away might see a different pattern. They might not see the same cold spot, or they might see it from another perspective, depending on their location and the true three-dimensional nature of the underlying fluctuation. This reminds us that cosmology is both universal and local. The laws apply everywhere, but our observations come from one position in space and time. We are cosmic detectives standing at one point, reconstructing the whole story from light that reaches us. The cold spot also forces us to think about the word explain. In everyday language, to explain something often means to tell a neat story, but in science, an explanation must make predictions, fit data, survive tests, and connect with other knowledge. Saying it is a supervoid is not enough. The void must have the right size, depth, distance, and effect. Saying it is inflation is not enough. The inflation model must produce the right statistical signature without ruining the rest of the CMB. Saying it is another universe is not enough. There must be a way to test that idea against the sky. Real explanation is strict. It demands more than imagination. This strictness is why the cold spot remains unresolved. Many ideas can tell a story. Fewer can satisfy the data. The random fluctuation explanation fits the standard model, but feels somewhat unsatisfying because the feature appears rare. The supervoid explanation is physically grounded but may be too weak alone. Exotic early universe explanations are exciting but not strongly confirmed. Multiverse collision ideas are dramatic but speculative. Each path opens a door, and each door leads to a wall of uncertainty. Yet uncertainty is not failure. In science, uncertainty is the landscape where discovery happens. The cold spot does not weaken cosmology by existing. It strengthens the scientific process by forcing cosmologists to sharpen their tools, improve surveys, question assumptions, and refine statistical methods. A universe with no puzzles would be a universe where curiosity had nowhere to go. The cold spot is a gift because it resists easy answers. There is another twist in this story. The cold spot may be teaching us about the limits of human intuition. We evolved to understand objects, surfaces, motion, danger, food, faces, and weather. We did not evolve to understand random fields on a sphere, inflationary quantum fluctuations, or microwave photons traveling for nearly 13.8 billion years. When we see a large cold patch, our intuition wants a cause like a physical object, a hole, a shadow, a scar. But the universe at this scale is governed by statistics as much as by objects. Sometimes the thing we're trying to explain is not a thing in the ordinary sense, but an unlikely arrangement in a random field. This does not make the mystery less real. A statistical anomaly can still be meaningful, but it changes how we think about it. The cold spot may not be a hidden object waiting to be photographed. It may be a rare configuration of primordial fluctuations. It may be a probability question, not a location question. That is difficult for the imagination, but essential for cosmology. Still, we can picture it poetically. A vast, cool island in the oldest light. A region where the baby universe whispers at a slightly lower temperature. Around it, the CMB has warmer and cooler patches, but this one draws the eye. It is as if the map of creation has a quiet bruise. It does not glow. It does not move. It does not announce itself. It simply remains, year after year, analysis after analysis, asking the same question: am I chance or am I evidence? To answer that, scientists simulate universes. They create artificial CMB skies based on the standard model, using random fluctuations with the same overall statistical properties. Then they search those simulated skies for features like the cold spot. If many simulations produce similar spots, the cold spot becomes less surprising. If very few do, it becomes more significant. But even this process depends on definitions. What counts as similar? Same temperature, same angular size, same shape, same surrounding hot ring, same wavelet statistic. Different choices produce different significance estimates. The mystery is not just in the sky, it is also in how we ask the sky questions. One common method used to detect the cold spot involved wavelets, mathematical tools that can identify features at particular scales. A wavelet is like a lens that focuses on structures of a certain size. When applied to the CMB, it can highlight unusual regions. The cold spot appeared strongly in such analyses, but because the method itself selects scales and features, scientists must carefully account for selection effects. Again, the cold spot is not a simple yes or no puzzle, it is a dialogue between data, mathematics, and interpretation. Foregrounds add another layer. The CMB is ancient, but between us and it lies the Milky Way, filled with dust, gas, magnetic fields, and radiation. There are also extragalactic sources, galaxy clusters, and other emissions. CMB experiments observe at multiple frequencies, so they can separate the true CMB from foreground contamination. Planck's frequency coverage helped enormously. The cold spot's persistence after foreground cleaning suggests it is not simply a dirty patch from our galaxy. But foreground removal is never trivial. Scientists must always ask whether residual contamination could influence anomalies, especially on large scales. The cold spot is in a region away from the brightest central band of the Milky Way, which helps. But away from the galactic plane does not mean completely free of foregrounds. Space is messy. Dust emits, electrons scatter, radio sources shine. Our own motion through the universe creates a dipole in the CMB that must be removed. Every map is a carefully processed product, not a raw photograph. The fact that the cold spot survives many processing methods is significant, but caution remains part of the story. There is also the question of gravitational lensing. As CMB photons travel through the universe, matter bends their paths slightly. Large-scale structure lenses the CMB, subtly distorting the pattern. Planck and other experiments can measure CMB lensing, giving information about the distribution of matter. In principle, lensing maps and galaxy surveys can help test whether a large underdensity lies along the cold spot direction. If a supervoid is there, it should leave traces in the distribution of galaxies and lensing signal. But again, the results are not simple enough to close the case. What would it take to solve the cold spot? Better galaxy surveys could map the matter distribution in that direction more completely. Deeper surveys could identify faint galaxies and measure distances more accurately. Improved CMB polarization data could help determine whether the anomaly is primordial. If the cold spot was present at the last scattering surface, it might have corresponding polarization patterns. If it was created mainly by a late-time effect like the integrated Sachs-Wolf effect, the polarization relationship could differ. This is one reason the future CMB observations matter. Temperature maps started the mystery, but polarization may help judge its origin. CMB polarization is like an extra layer of the ancient message. When photons last scattered from electrons in the early universe, their light became slightly polarized depending on local conditions. This polarization contains information about the same early plasma, but in a different form. If temperature anomalies are like the brightness pattern of the baby universe, polarization is like the direction of its ancient light waves. Comparing the two can reveal whether a feature belongs to the primordial surface or was added later during the photon's journey. The cold spot's full answer may be hidden not only in how cold it is, but in how its light is polarized. Future surveys of large-scale structure will also matter. Projects that map galaxies, weak lensing, and cosmic expansion can refine our view of voids. If the Eridanus region contains a supervoid, future data may reveal its true shape and mass deficit. If the underdensity is too small, the void explanation may weaken. If it is larger or more complex than currently known, it may strengthen. Science moves with instruments. Mysteries that seem philosophical today can become measurable tomorrow. But even if future data shows a void contributes to the cold spot, one question may remain: why is there such a large void there? Cosmic voids naturally form in the cosmic web. Under dense regions expand faster relative to dense regions because they have less gravity holding matter together. Over billions of years, matter flows out of voids toward filaments and clusters, so a supervoid itself is not impossible. But an extremely large, extremely deep void would also be statistically interesting. The universe can produce vast structures, but their frequency and properties test cosmological models. Thus, the cold spot mystery may shift from the CMB to the distribution of galaxies. There is a subtle emotional difference between a mystery that points to new physics and a mystery that points to rare structure. New physics feels more dramatic. A giant void feels more understandable, but both are profound. A void, hundreds of millions or billions of light-years in scale, is not ordinary in human terms. It is a region so vast that entire galaxies become sparse dust within it. If the cold spot is connected to such emptiness, then we are seeing how the largest structures in the universe can gently alter the oldest light. The word void can mislead us. It suggests nothingness, but cosmic voids are not absolute nothing. They contain dark matter, faint galaxies, gas and radiation. They are underdense, not empty. Even the emptiest cosmic spaces are filled with the CMB, neutrinos, gravitational fields, quantum fields, and the expansion of space itself. The universe does not seem to offer true nothingness. Even its emptiness has structure. That makes the idea of a cold spot caused by a void especially poetic, a region that is not nothing, but less than average, leaving a faint chill on ancient light. Now let us return to the idea of random fluctuation, because it may be the most scientifically conservative answer, and also the hardest to emotionally accept. In a Gaussian random field, which is often used to model primordial fluctuations, rare peaks and troughs occur naturally. A large cold region can appear just by chance. If you generate enough random skies, some will have features that look impressive. Our universe could simply be one of those. There is no rule that the observed sky must look perfectly typical in every way. In fact, because there are many ways to be unusual, some unusual feature is almost expected. This is humbling. Humans often think that mystery must have a special cause, but randomness is not lack of causation. In physics, random initial fluctuations can have well-defined statistical origins. Quantum fluctuations during inflation are not meaningless. They are part of the physical process that created structure. If the cold spot is random, it is still a fossil of quantum uncertainty stretched across cosmic scales. That is already astonishing. A quantum fluctuation, once smaller than an atom in some inflationary picture, may have become a vast cold pattern in the sky. Random does not mean unimportant. It means the universe rolled its primordial dice, and this is one face we happen to see. The phrase primordial dice is not just metaphor. Quantum theory tells us that certain physical outcomes are probabilistic. Inflation, if it occurred as widely believed, magnified tiny quantum fluctuations into macroscopic density variations. The galaxies are, in a deep sense, descendants of quantum uncertainty. The cold spot, if random and primordial, may be one of the largest visible expressions of that fact. It would be a reminder that the structure of the universe was not drawn with perfect symmetry, but seeded by microscopic uncertainty in the earliest moments. This makes the cold spot more beautiful, not less. Even if it is not a portal to another universe, even if it is not a cosmic texture, even if it is not fully caused by a supervoid, it is still a place where the deepest layers of physics become visible. It is a mark in radiation older than stars. It is a pattern connected to inflation, gravity, quantum fields, dark energy, and cosmic structure. Few mysteries can be so quiet and so enormous at the same time. Now consider the multiverse idea again, not as a claim, but as a window into why the cold spot became famous. The public imagination loves the idea that a cold region might be a collision scar from another universe. It turns a statistical anomaly into a cosmic drama. But science must ask, what would a bubble collision actually look like? Would it produce a circular temperature feature? Would it create polarization patterns? Would there be multiple imprints? How likely would such a collision be? Would the rest of the CMB remain as observed? These questions are difficult. Without clear predictions and evidence, the idea remains speculative. Still, speculative ideas have a place when clearly labelled. They push theorists to ask what observations could reveal about regions beyond our direct reach. Inflation itself was once a bold idea, and now it is deeply integrated into cosmological thinking, though its exact mechanism remains unknown. The multiverse may or may not be physically real. The cold spot may or may not have anything to do with it, but the fact that one cold patch can lead to questions about other universes shows how powerful CMB observations are. A tiny temperature anomaly can pull the mind toward the boundaries of existence. The cold spot also reminds us that the universe may contain information we're not yet wise enough to decode. Ancient people looked at the sky and saw myths. Early astronomers saw moving lights and built geometry. Newton saw gravity shaping orbits. Einstein saw space-time curvature. Modern cosmologists see quantum fluctuations, dark matter, and microwave anisotropies. Each generation reads the same sky at a deeper level. Perhaps future scientists will look back at the cold spot and say it was an obvious clue, or perhaps they will say it was a beautiful accident. We do not know yet. There is a meditative feeling in that uncertainty. We live in a universe where not every question has been closed. The night sky is not a museum of solved facts. It is an active frontier. Even the oldest light still holds secrets. Even after satellites orbit Earth, after supercomputers simulate cosmic history, after equations describe the early plasma, one cold region remains difficult to explain. That should not frustrate us. It should awaken us. The cold spot is sometimes presented as if it breaks cosmology. That is not accurate. The standard cosmological model remains one of the most successful scientific models ever created. It explains the broad CMB pattern extremely well. It predicts the distribution of primordial elements. It fits many observations of large-scale structure. The cold spot is not a fatal wound. It is more like a small but persistent question mark written in the margin of an otherwise extraordinary theory. And margins matter. Sometimes the future of science begins in the margins. When scientists say an anomaly has a certain probability, such as being unlikely at a few % level or less depending on the analysis, that does not mean it is impossible. A 1% event happens one time in 100. If there are many possible 1% features to notice, finding one becomes less shocking. This is why responsible scientists avoid exaggerated claims. The cold spot is interesting, not definitive. It motivates investigation, not conclusion by excitement. Let us imagine standing outside on a dark night, looking toward the region of Eridanus. Your eyes see stars, perhaps only a few depending on your sky. But behind those stars, behind the Milky Way's faint structures, behind galaxies too dim to see, ancient microwave photons are arriving. They have crossed almost the entire observable universe. They began their free journey before Earth existed, before carbon was forged in stars, before the Milky Way had its familiar shape. They travelled while the first stars ignited, while galaxies merged, while black holes grew, while planets formed, while life arose, while human minds evolved enough to build instruments that could finally notice them. And when those photons reached us, they told us, in this direction the early light is slightly colder. That is a staggering chain of events. The cold spot is not just a data feature, it is a meeting between the beginning of the universe and the consciousness of creatures made from star-made atoms. The photons did not know they were carrying a mystery. They simply moved through space. But we, with our fragile instruments and restless curiosity, turned their temperatures into a question. The coldness itself is incredibly small. The CMB's average temperature is about 2.725 Kelvin. The anisotropies are on the scale of about 1 part in 100,000. If the CMB were represented as a calm ocean, the temperature ripples would be extremely tiny waves. Yet those tiny waves shaped everything. This is one of the great paradoxes of cosmology. The universe is structured because of almost invisible differences. The difference between a future galaxy cluster and a future void began as a microscopic imbalance in the early universe. The cold spot belongs to that world of tiny differences with enormous consequences. The cold spot also invites us to think about what large means. On Earth, a mountain is large, a continent is larger, a planet is enormous, a star is almost unimaginable. A galaxy contains hundreds of billions of stars. But the cold spot is an angular feature on the CMB, corresponding to scales so vast that ordinary intuition fails. If primordial, It may relate to a region on the last scattering surface spanning billions of light years in today's expanded scale. If connected to a supervoid, the structure may be hundreds of millions of light years across or more. Either way, it belongs to the largest meaningful patterns we can discuss. At such scales, the universe becomes less like a collection of objects and more like a field of probabilities and densities and curvature. There are no edges you can touch. There are gradients, correlations, power spectra, and statistical distributions. The cold spot is a feature in that grand field. It is an invitation to leave behind everyday thinking and enter cosmic thinking. One of the deepest questions is whether the cold spot violates isotropy, the idea that the universe looks statistically the same in all directions. A single cold region does not necessarily violate isotropy. Random isotropic universes still contain hot and cold patches. But if the cold spot is part of a broader pattern of preferred directions or large-scale asymmetry, then the question becomes more serious. Some CMB anomalies have been discussed in relation to possible departures from perfect statistical isotropy, but evidence remains debated. The universe appears highly isotropic overall, especially in the CMB. Any departure must be subtle. Subtle does not mean unimportant. Einstein's general relativity began with subtle inconsistencies in older physics. Quantum mechanics emerged from subtle failures of classical ideas. In precision science, small deviations can matter deeply, but they can also be noise. The cold spot stands at this crossroads, subtle enough to be uncertain, persistent enough to be intriguing. Let us explore cosmic topology for a moment. The universe may be spatially infinite, or it may be finite but unbounded, like a higher dimensional version of a surface where traveling far enough could bring you back to your starting region. Different topologies could, in principle, leave patterns in the CMB, such as repeated circles or correlations. Some have wondered whether anomalies could hint at non-trivial cosmic topology. Searches for clear signatures have not found strong evidence. The cold spot alone does not prove topology. But it belongs to the larger question of the universe's global shape, one of the most profound questions science can ask. What is the shape of all space? Does it go on forever? Does it curve back on itself? Is the observable universe only a small patch of a much larger reality? The CMB helps answer these questions because it is the farthest light we can see. Measurements suggest the observable universe is very close to spatially flat, at least within current precision. But flatness does not necessarily mean infinite. A flat universe can still have certain finite topologies. Again, the cold spot does not solve this. It simply reminds us that the larger scales remain mysterious. The cold spot also intersects with the question of dark energy. If the supervoid explanation depends on the integrated Sachs-Wolf effect, then the effect itself depends on the accelerated expansion of the universe. Dark energy is already one of the biggest mysteries in physics. We give it a name, we measure its influence, but we do not truly understand what it is. It may be vacuum energy. It may be a cosmological constant. It may be something dynamic. It may point to deeper gravitational physics. If a void's effect on CMB photons contributes to the cold spot, then this anomaly indirectly touches dark energy too. There is something almost cinematic about that connection. The oldest light in the universe travels through a giant emptiness, while the accelerated expansion driven by dark energy subtly changes the gravitational landscape, causing the light to lose a little energy before reaching us. The cold spot, in this view, is not just about coldness. It is about time, gravity, emptiness, and the fate of cosmic expansion. If dark energy continues to accelerate the universe's expansion forever, distant galaxies will eventually move beyond our observable reach. Future observers in the far future, if any exist, may see a much emptier sky. The CMB will be stretched to longer wavelengths, colder and harder to detect. The cosmic web beyond local bound structures will fade from view. We live in a special era when the CMB is still observable, and galaxies are still visible across vast distances. The cold spot is a mystery available to our cosmic moment. It may not be accessible forever in the same way. This gives the story a quiet urgency. The universe is not only expanding, it is changing what can be known. Cosmology is possible because we exist at a time when the evidence is still present. The cold spot is part of that evidence. It is a message from a universe that will not always speak so clearly. Now, let us consider the emotional power of ancient light. Every CMB photon began its free journey when the universe became transparent. That photon has traveled through expanding space for about 13.8 billion years. Because space expanded during its journey, its wavelength stretched enormously. What began as much hotter radiation is now microwave light. This stretching is not because the photon got tired in an ordinary sense. It is because the fabric of space expanded, stretching the wavelength along with it. The universe itself cooled the light. The cold spot photons are only slightly less energetic than the average CMB photons, but that tiny difference may encode gravitational conditions from the early universe or later cosmic structures. It is like receiving an ancient letter where one word is written faintly differently, and that difference may reveal the hand that wrote it, the weather it traveled through, or a hidden event in the sender's world. This is why scientists do not ignore the cold spot. Precision matters. The universe often hides its biggest truths in small measurements. The expansion of the universe was discovered through redshifts. Exoplanets are found through tiny dips in starlight or small stellar wobbles. Gravitational waves stretch and squeeze space by fractions smaller than an atomic nucleus across kilometer-scale detectors. The CMB Cold Spot is another example, a tiny temperature difference opening a vast question. The story of the cold spot is also a story about humility. For most of human history, we did not know the CMB existed. We did not know galaxies were outside the Milky Way. We did not know the universe had a beginning in a hot, dense state. We did not know dark matter or dark energy existed. Again and again, the universe has been larger, older, stranger, and more subtle than our ancestors imagined. The cold spot may be another subtle hint that our current picture, though powerful, is not complete in every detail, but we must not turn humility into fantasy. The right response to mystery is disciplined wonder. Disciplined wonder means we allow ourselves to feel awe, but we do not invent certainty. We can say the cold spot is strange. We can say it may be random. We can say a supervoid may contribute. We can say exotic explanations have been proposed. We cannot honestly say it proves another universe. We cannot say it proves cosmology is wrong. We cannot say scientists have no idea at all. The truth is more interesting than exaggeration because the truth is still unresolved. The cold spot's location in Eridanus has symbolic beauty too. Eridanus is often imagined as a celestial river. In ancient sky traditions, it represented a river flowing through the heavens. And in that direction, modern science finds a cold stream in the oldest light. Of course, the constellation is just a human pattern projected onto stars at different distances. It has no physical relation to the CMB anomaly, but the poetry is hard to miss. A cosmic river, and inside it, a cold mystery. When we speak of the cold spot as being in Eridanus, we are using sky coordinates, not saying it is near those stars. The stars of Eridanus are in our galaxy, relatively nearby compared with the CMB. The cold spot's light comes from the edge of the observable universe, or its effect may involve structures along that line of sight. This distinction is important. The sky compresses depth into direction. A constellation is a foreground pattern. The cold spot is a deep cosmic signal behind it. Depth is one of the hardest things to feel when looking at the sky. Your eye sees a flat dome. Science reveals layers: airplanes, satellites, planets, stars, nebula, galactic arms, nearby galaxies, distant quasars, the cosmic web, the CMB. The cold spot belongs to the deepest visible layer. It is not part of the familiar night sky, yet it is present behind every visible thing in that direction. If we could see microwaves with our eyes and remove all foregrounds, the entire sky would glow with the CMB. It would not look black. It would look like a nearly uniform ancient light, with tiny mottled variations. The cold spot would be one subtle region in that glow. It would not be dramatic to the eye unless artificially enhanced, as CMB maps usually are. Those colourful maps exaggerate tiny differences so humans can see them. Red and blue on CMB maps do not mean hot like fire and cold like ice. They mean microkelvin variations around an already extremely cold average. This matters because images of the cold spot can mislead. A dark blue patch may look like a cosmic hole or frozen region. In reality, it is a statistical temperature feature in microwave radiation. The drama is not visual violence, it is scientific subtlety. The universe's deepest mysteries do not always look explosive. Sometimes they look like a slight imbalance in an ancient glow. The cold spot may also help us teach the difference between observed fact and interpretation. Observed fact: there is a cold region in the CMB maps. Interpretation 1: it is a random fluctuation. Interpretation 2: it is influenced by a supervoid. Interpretation 3: it reflects early universe physics. Interpretation 4: it may involve exotic scenarios. A healthy scientific mind separates these layers. Confusion happens when interpretation is presented as fact. Good cosmology keeps them distinct. Let us now imagine the cold spot as a detective story. The victim is certainty. The crime scene is the microwave sky. The suspects are randomness, a supervoid, inflationary features, cosmic textures, topology, foregrounds, and speculative bubble collisions. The evidence includes WMAP maps, Planck maps, galaxy surveys, simulations, statistical analysis, and polarization data. Some suspects have alibis, some have motives but weak evidence, some are dramatic but unlikely. The detective is science itself, patient, skeptical, and unwilling to close the case too early. Randomness says, "I was always allowed." Rare things happen. The supervoid says, "I was in the right direction and I can cool photons a little." Inflation says, "The earliest moments may have had features you have not understood." Cosmic texture says, "The early universe may have left defects." The multiverse says, "Perhaps your universe is not alone." Foregrounds say, "Maybe your instruments and galaxy confused you." And science replies, "Show me the numbers." That is the heart of the mystery. Show me the numbers. Not the most exciting story, not the most viral headline. The numbers. How cold, how large, how significant, how robust across maps, how correlated with structure, how consistent with simulations, how predicted by theory, how testable by future observations. The cold spot survives because the numbers are interesting enough to continue the conversation. One thing that makes cosmology different from many laboratory sciences is that it studies events we cannot repeat. We cannot recreate the Big Bang. We cannot move galaxies around to test voids. We cannot build another universe. Instead, cosmology relies on observation, theory, simulation, and consistency. It is like archaeology, but the ruins are made of light, gravity, and matter distribution. The cold spot is an artifact in this cosmic archaeology. It may be a broken shard from the early universe, or it may be a stone shaped by later weather. Either way, it must be examined with care. The cold spot also reveals the power of full sky observation. If scientists had only measured small patches of the CMB, they might not have noticed large-scale anomalies. To see the biggest patterns, you need the whole sky. This is why satellites like WMAP and Planck were so important. Ground-based telescopes can be extremely powerful for small-scale CMB measurements, but the largest angular scales require broad sky coverage and careful control of systematics. The cold spot is a large-scale feature, so it belongs to the era of cosmic cartography. Cosmic cartography is the mapping of everything: radiation, galaxies, dark matter through lensing, gas through X-rays and radio signals, gravitational waves, neutrinos perhaps in the future. The more maps we have, the more we can compare. A feature in one map may be explained by another. A cold region in the CMB may correspond to a void in galaxy maps. A lensing deficit may reveal less matter. A polarization pattern may point to primordial origin. The future of the cold spot depends on multi-map cosmology. There is a philosophical depth here. The universe is not understood through one sense alone. Just as humans understand the world through sight, sound, touch, and memory, cosmologists understand the universe through different messengers, light at many wavelengths, gravitational waves, particles, and large-scale structure. The cold spot is one note in the microwave messenger. To understand it, we may need the harmony of other messengers. If it turns out to be a random fluctuation, some may feel disappointed, but they should not. A random primordial cold spot would still be a magnificent confirmation that the early universe's quantum statistical nature can create features on unimaginable scales. It would show that our universe, though statistically ordinary overall, contains individual peculiarities. It would be like learning that a face has freckles not because each freckle has a dramatic story, but because biology naturally creates variation. The freckles still make the face unique. If it turns out to be a supervoid effect, That too would be remarkable. It would mean the cold spot is a visible interaction between the CMB and the cosmic web, a sign that large-scale structure and dark energy subtly modify ancient light. It would connect the earliest observable universe with relatively late cosmic evolution. It would be a lesson in how no light travels through an untouched universe. Every photon carries not only its origin but its journey. If it turns out to require new early universe physics, the implications would be profound. It could mean inflation had features, or that fields behaved unexpectedly, or that our assumptions about primordial fluctuations need refinement. This would not necessarily destroy the standard model, but it could extend it. Many great scientific advances do not replace old theories completely. They deepen them. General relativity did not make Newton useless for everyday gravity. It revealed a deeper layer. Quantum mechanics did not make classical mechanics useless. It revealed its limits. A true cold spot breakthrough might do something similar for cosmology. If it somehow pointed toward a multiverse or bubble collision, the implications would be almost beyond imagination. But because the claim would be so extraordinary, the evidence would need to be extraordinary too. A single, ambiguous anomaly is not enough. Science would require additional signatures, consistency with theory, and exclusion of simpler explanations. Until then, the multiverse remains a fascinating but unproven possibility, not a conclusion. There is another possibility. The cold spot may never receive a perfectly satisfying answer. Some cosmic features may remain probabilistic. We may reduce uncertainty but not eliminate it. Because we have only one observable universe, some questions may always have a residue of ambiguity. This is not failure. It is part of studying the cosmos from within. We are not outside observers with infinite samples. We are inhabitants of one cosmic realization, trying to infer the rules from the one sky above us. This limitation can feel frustrating, but it is also beautiful. The universe is not a laboratory specimen under glass. It is our home, our origin, our horizon. We study it while being part of it. The atoms in our brains were forged by stars that formed from primordial fluctuations like those seen in the CMB. The universe created the conditions for observers, and those observers now analyze the universe's baby picture. The cold spot is one part of that self-reflective cosmic loop. Let us think about scale again in a more intimate way. The CMB photons reaching a detector on Earth are weak. They arrive from every direction. Instruments must be cooled, calibrated, shielded, and corrected for motion. The signal is faint but everywhere. A spacecraft like Planck scanned the sky again and again, building a map from tiny measurements. Human teams spent years processing the data. Equations turned detector readings into cosmological parameters. And inside that immense technical effort, a cold region remained visible. The mystery is not just cosmic. It is also a triumph of human precision. There is a tenderness in that. We are small creatures on a rocky planet, but we can measure millionths of a degree in radiation from the beginning of the universe. We can argue about whether a structure billions of light years wide made ancient photons slightly colder. We can compare our sky to simulated universes inside computers. We can ask whether a cold patch is a random quantum fossil or a sign of something deeper. That is one of the most amazing facts in all of science. The cold spot also shows that empty space is not simple. The region between galaxies may seem empty, but it contains gravitational potentials, dark matter distributions, dark energy dynamics, and relic radiation. A photon crossing a void experiences the universe's expansion and curvature. Space is active. It is not a stage where objects move. It is part of the physics. General relativity taught us that matter and energy shape spacetime, and spacetime guides motion. The cold spot, if connected to a void, is a subtle demonstration of that relationship. In everyday life, cold means lack of heat. In the cold spot, cold means slightly lower photon energy, compared with the average CMB. This difference is measured after removing effects like our motion relative to the CMB. Our solar system moves through space, and this motion creates a strong dipole. The CMB appears slightly hotter in the direction we move and colder behind us. Scientists subtract this dipole to study the smaller primordial variations. Only after careful correction do features like the cold spot stand out. This reminds us that even our motion must be accounted for before we can read the universe correctly. We are not stationary observers. Earth orbits the Sun orbits the Milky Way. The Milky Way moves within the local group. The local group moves relative to the CMB. Every measurement is made from motion, yet science can correct for these motions and reconstruct a cosmic rest frame defined by the average CMB. In that frame, the cold spot remains a feature. The universe lets us find orientation even while we are moving through it. The cold spot's existence also challenges simple emotional narratives. Sometimes people want space mysteries to have dramatic answers, aliens, portals, other universes, hidden forces. But the real drama of the cold spot is quieter and deeper. It is the drama of uncertainty at the edge of measurement. It is the drama of a successful theory confronted by a persistent oddity. It is the drama of scientists refusing both exaggeration and dismissal. It is the drama of a universe that is comprehensible, but not completely conquered. A good scientific mystery should not make us abandon reason. It should make reason more alive. The cold spot does exactly that. It forces us to ask what counts as evidence, how to handle rare events, how to compare models, how to avoid bias, how to combine data sets, and how to speak honestly about uncertainty. These are not side issues. They are the core of scientific thinking. Now let us drift deeper into the early universe, where the seeds of the CMB were born. Inflation, if correct, happened extremely early, far before the CMB was released. During inflation, space expanded exponentially, smoothing the universe and stretching quantum fluctuations. After inflation ended, the universe reheated, filling with particles and radiation. Over time, it cooled, forming protons, neutrons, nuclei, atoms, stars, and galaxies. The CMB came after the formation of light nuclei but before stars. It is a snapshot of the universe when matter and radiation parted ways. The cold spot, if primordial, may have its roots in the inflationary era, not merely at recombination. That means it could be connected to physics at energy scales far beyond what particle accelerators can reach. The CMB becomes a natural particle physics experiment conducted by the universe itself. We cannot directly build an inflation machine, but we can observe inflation's possible fingerprints. This is why anomalies are tempting. They may be clues to ultra-high energy physics. But inflation itself is not one model. It is a family of models. Some are simple, some are complex, some predict nearly Gaussian, nearly scale-invariant fluctuations. Observations support this general picture strongly, but the exact mechanism remains unknown. A cold spot-like anomaly might be accommodated by special inflationary features, but adding features risks making a theory less elegant or less predictive. Scientists must avoid building a model only to explain one oddity while ignoring the rest. A good model must explain the cold spot without breaking everything else. This is like tuning a musical instrument. If you adjust one string to fix one note but ruin the harmony, the solution fails. The CMB is the full symphony. The cold spot is one unusual note. Any theory that explains it must still match the entire cosmic composition. Cosmic textures face a similar challenge. They can create localized CMB features, but they must also fit constraints from the absence of other expected signals. If topological defects were common or strong, they might leave many imprints, distort the power spectrum, or produce gravitational waves. Observations limit these possibilities, so a texture explanation must be carefully tuned and supported. Fascinating, yes. Established, no. The supervoid explanation also must match several observations at once. It must match galaxy counts, redshift distribution, lensing, and expected ISW temperature shift. It must explain the angular size and depth of the cold spot. It must be more convincing than chance alignment. This is difficult but not impossible. The debate continues because the evidence is complex. There are also alternative statistical approaches. Some researchers examine whether the cold spot is anomalous in temperature alone, or in kurtosis, or in wavelet space, or in the presence of a surrounding hot ring. The more specific the feature, the more unusual it may seem, but also the more vulnerable it becomes to after-the-fact selection. This is a subtle balance. If you define the anomaly too broadly, it may not be significant. If you define it too narrowly after seeing it, you may inflate significance. Good science must walk between these errors. The cold spot is therefore not only a cosmological puzzle but a lesson in statistics. In a universe of data, significance is not always intuitive. A beautiful anomaly may be less significant than it looks. A boring pattern may be deeply meaningful. Scientists must quantify surprise. They must ask what they would have expected before seeing the data. This discipline is what separates science from storytelling, and yet, storytelling has its place when it respects truth. The cold spot deserves a story because it connects facts into meaning. It begins with the Big Bang's afterglow, passes through satellite maps, enters statistical debate, touches giant voids and dark energy, opens doors to inflation and speculative multiverses, and ends in uncertainty. That is not fiction. That is the real shape of modern cosmology. Perhaps the most mysterious thing about the cold spot is not that it is cold, but that it is understandable enough to be mysterious. If the universe were completely chaotic, no anomaly would matter. If we had no standard model, we would not know what was unexpected. The cold spot is strange because the rest of cosmology works so well. An anomaly needs a background of understanding. The better our theory, the sharper the mystery becomes. This is similar to hearing one wrong note only because you know the melody. The standard model gives cosmology its melody. The cold spot is a note that may be slightly off. Without the melody, we would not notice. With the melody, we cannot ignore it. The cold spot also invites a deeper question. How much of the universe is knowable? The observable universe is limited by the speed of light and cosmic age. Beyond our horizon may lie regions forever inaccessible. If inflation occurred, the entire universe may be vastly larger than what we can see. The CMB is the boundary of direct electromagnetic observation, not because nothing exists beyond it, but because before recombination the universe was opaque to light. We cannot see earlier with photons. We infer earlier times through theory and indirect signals. The cold spot sits on that boundary, where observation meets inference. Maybe the cold spot is telling us about something beyond the horizon. Some theories of bubble collisions or super-horizon perturbations involve influences from scales larger than the observable universe. This is difficult to test, but conceptually profound. Our observable patch may not contain the full explanation for every large-scale feature. The universe we see could be part of a larger structure. Again, this is speculation unless supported by evidence, but it shows why the cold spot touches the edges of cosmological thought. The idea of super-horizon modes means fluctuations larger than our observable universe could affect the CMB in subtle ways. Inflation can stretch fluctuations beyond the horizon. Some large-scale anomalies might in principle relate to such modes, but proving this is extremely difficult because by definition, we cannot observe the full wavelength. The cold spot may be entirely within standard random fluctuations, but its scale naturally leads to these questions. There is a tension between humility and ambition. Humility says, do not claim more than the data supports. Ambition says, do not stop asking bold questions. The cold spot needs both. Without humility, it becomes pseudoscience. Without ambition, it becomes a dismissed oddity. The best science holds wonder and caution together. Let us imagine a future CMB mission with better polarization sensitivity, better control of foregrounds, and full sky precision. It studies the cold spot carefully. It finds a polarization pattern matching a primordial temperature fluctuation. That would strengthen the random or early universe explanation. Or imagine it finds polarization inconsistent with a primordial origin, while galaxy surveys map a massive underdensity perfectly aligned with the spot. That would strengthen the void explanation. Or imagine it finds additional subtle patterns around the cold spot predicted by a specific early universe model. That could open new physics. The mystery is not frozen forever. It is waiting for sharper questions. Until then, the cold spot remains a cosmic maybe. Maybe chance, maybe void, maybe primordial feature, maybe something not yet imagined. In science, maybe is not weakness when it is honest. It is the space where future knowledge grows. The cold spot also reminds us that the universe contains both simplicity and complexity. The CMB's average temperature is simple, a nearly perfect blackbody. The power spectrum is mathematically elegant, but the actual sky has individual features, asymmetries, and anomalies. Nature often behaves this way. Laws are simple. Outcomes are rich. A snowflake follows basic physics, yet each snowflake has a unique pattern. A galaxy follows gravity and gas dynamics, yet each galaxy has its own history. The CMB follows statistical laws, yet our sky has its own cold spot.